Okay, so last time we were doing like max flow, min cut, and Menger's theorem and stuff. We didn't prove the max flow, min cut theorem, so I'll just start with that today, and then then we'll move on to talk about algorithms for finding max flows. This is just the statement again. Basically, the max value of a flow from S to T is equal to the minimum capacity of an ST cut. Okay, so then there's Menger's theorem again. We've got a digraph. So these are very similar statements. Well, the max flow min cut seems to be more general, but actually it's going to turn out that it's basically, they're kind of the same thing. So anyway, we've got a digraph. We've got two vertices in the vertex set of D. So I can say this as either there exists, like for any k, either there exist k disjoint paths from S to T, or there exists an ST cut U with the number of edges leaving U at most k minus 1. Okay. In case you don't remember what an ST cut is, so it's a subset of the vertices. It's just a subset where like U is in, or S is in U and T isn't. So and this like boundary thing, like this symbol thing with the plus, is just the arcs pointing. It's a set of all arcs pointing out of U. So if I've got U, then it's like the arcs that have one endpoint, like the arcs that start in U and point outward, right? Okay. So yeah, we proved this thing last time, and now I want to use that to prove the max flow min cut theorem. Okay, maybe I'll start here. So proof of max flow min cut. So the first step is going to be to prove that the max flow is at most the min cut, and then we'll prove the opposite. Yeah. Oh, I see. Okay. Do it here. Okay. Thanks. Yeah, what did I? Oh, I guess, well, yeah, T is, in the vertices out, well, T is always a vertex of the thing. Did you mean like, yeah. I guess what I wrote was, I mean, maybe I was being a bit lazy, but it kind of means the same thing. It's because T is already a vertex of the digraph, so like S should be in U and T should be not in U, which is, the same thing as it's in the complement, but yeah. Or is there any other problems with this? I might have. Okay, yeah. Yeah, it's just some set that has S in it and T outside of it. Okay, so first we're going to prove the easy direction, which is that the max flow is at most the min cut. Okay. Or in other words, what this says is that for every flow, because, yeah, so for any flow and any cut, the value of the flow is at most the value of the cut, because then if I take the maximum and the minimum, yeah, it kind of goes that way. This isn't trivial, but this is kind of this should be the easy direction. It's kind of saying that, like, you know, if there's some kind of a bottleneck, like there's some kind of set where, like, to exit that set, you would have to, with a high flow, you'd have to violate the capacities leaving that set. Then, like, that cannot, you know, if I've got some kind of a, and I know that I only have capacity 1, you know, 2 or something, like, and S is inside of here and T is outside of here. I mean, I think it hopefully is kind of clear that, like, how would I, let's say I wanted to have a flow of value 6 from S to T. Like, how would I do that? I mean, all of the flow has to, like, somehow leave this set, and if there's only capacity 5, then you couldn't do it, right? But anyway, let's do this sort of formally. So let F be a flow, and let U be an ST cut. Okay. So let's remember what the value of a flow is. That's basically like the net amount of flow coming out of S. So it's the sum over all vertices in the out neighborhood of S of the flow from S to V minus the sum over all vertices in the in neighborhood of S of the flow from V to S. This is just by definition. This is like how much stuff is coming out of S. Of course, like, if there's some stuff going into S, then you should subtract that because it doesn't really count, right? Okay, I claim that this is equal to the sum over all U in U of the sum over all V in the out neighborhood of U of F U V. So basically I'm replacing, so this was just for S, and I'm replacing this with a sum that goes over all vertices of U. And we're going to have to justify this. So now I'm summing over the in neighbors of U and doing F of VU. I feel like intuitively this makes sense, but like, actually, with how, like, if we think of the actual algebra here, like, can anyone see, like, why this makes sense? Something to do with this, like, funny, you know, there's this, like, flow condition at every vertex, except for S and T. You should have the amount of flow in equals the amount of flow out, right? So somehow that's coming into play here. Yeah, do you see how it works?
The first line is the amount of, like, it's round.
Yeah, that's like my intuition anyway, as well. But so, like, in terms of the actual algebra, how do you show that these are the same? Like, it's actually not too bad because it's, okay, consider the case when this little u is equal to S, okay? Well, then that's the same as this, right? When u is equal to S, I'm counting this in that sum. And then whenever u is not equal to S, well, it counts 0 because the flow out, for any vertex that's not out S, the flow out is equal to the flow in. So yeah, this is counting when u equals S, that counts, that gives me this. And when u is not equal to S, it gives me 0 because flow in equals flow out. So yeah, it's just adding a bunch of zeros. Um, okay, then I claim that this is the same as the sum overall UV in the kind of these kind of outward edges, like coming out of the set U of f of UV minus the sum overall edges pointing into the set. Okay. So still everything should be equal. And here I need to go from here to here, I need to kind of think of things in a bit of a different way. So I've got the set U, right? Some edges go out of U, some come in, and there's some edges inside, and then there's like edges out. Oh, whenever I'm saying edges, I mean arcs. Anyway, there's some arcs, yeah, inside, outside, whatever. Obviously, in this sum, the arcs that are completely outside are irrelevant. They're never getting counted. Any arc that starts inside and goes outside, like when this is the vertex U, like in this sum, I would count that here. So it'd be like a positive contribution. But I would never count it here because if this is, let's say, the vertex V, like V is not in U, so I don't count it in the negative side. Analogously, any edge like this, if I call that vertex U and this one V, like I count it, well, or maybe I should call this U because it's in U. Any arc like this, the flow value gets counted here, but not here. Any edge that's completely inside, like I'll count that this way and I'll count it this way, and it'll cancel. So really the only things that end up counting are the arcs that go out or the arcs that come into the set. Because yeah, I'll count the ones that are inside, I'll have a positive contribution and a negative that'll cancel out. Okay, so that ends up being that. But then, of course, I could just throw away this thing, right? And say that's at most the sum overall UV in this kind of these outward pointing edges of f of UV. But then since this is a flow with capacity C, this is at most the sum of the capacities. Okay. Okay, so that proves that the max flow is at most the min cut. Because yeah, this F could have been the max flow, and this cut U could have been the min cut, and then max flow would be at most the min cut. Questions about that? Okay. Okay, so now I claim that the max flow is at least the min cut. Okay. And this proof, I think, is it's going to be. I think it's a slightly unusual proof, although I don't know. I mean, basically, we're going to try to use Menger's theorem. But Menger's theorem is just talking about disjoint paths, right? Which are kind of like flows. They're kind of like 0, 1 valued flows, right? If I take, let's say I take K, let's say I take like 3 disjoint paths from S to T. And maybe the graph has, or the digraph has edges, has other edges, right? If you think of putting like a value of 1 on all of those edges, that would be like a flow from S to T of value 3. And if you put 0 on the other edges, then yeah, that would be it's kind of like a flow, right? But obviously, yeah, so this would be like a flow with a capacity function where every arc has capacity 1, right? So in particular, from the Menger's theorem, so So basically, we're going to kind of do this in cases in some sense. So if all of the arcs have, well, maybe even just one for all arcs. If they all have capacity 1, then we are done by Menger's theorem. Right, because actually a flow from S to T, yeah, if there's a flow of some weight or something, like that's going to correspond to just taking disjoint paths. So like either you're going to find, if you find a cut, like let's say we want to show that the value of this thing, well, okay, if you have a cut of size k minus 1, then you will not have k disjoint paths. Yeah, maybe I should have written this in the same way I wrote it last time. So what this says is that, what this really says is that the maximum number of disjoint paths equals the minimum size of a cut. So Menger's theorem could be written in that way. So basically, if you don't have a small cut, then you actually have disjoint paths, and the disjoint paths give you a flow. So yeah, in this case, it just boils down to Menger's theorem. So let's say now we're in the case where, let's say all of the capacities are positive integers. But in this case, like, we could still basically boil it down to this case because, if you've got a capacity of 3 on this arc, well, just replace this by 3 parallel arcs, okay? And then with each of them with capacity 1. Okay, if you're skeptical about, like, I don't know if we ever talked about having, parallel arcs between 2 vertices, but if you don't like this, then you could just say, okay, I could also just put like a vertex in each of them. And then obviously, like, having a flow, like if everything has capacity 1 here, having a flow like going like that would be the same as that, right? So because everything coming into this one has to come out of it. So anyway, that should work. So yeah, you basically just duplicate every arc as many times as you need, and then you assume all the capacities are 1. Okay, next case. Maybe I'll get you guys to help me with this one. Like, what would you do if the capacities were rational? The least common multiple? Yeah, exactly. So yeah, if people online didn't hear that, take all your capacities, take the least common multiple of all of the, denominators, multiply by that, solve the problem. It'll be an integer problem now. And then take your answer and divide it by that number again. And then, yeah, so we'll just multiply by, LCM of denominators, solve the integer problem, and then divide again. Okay, so then I guess the last case is like the general case where these things are real. Okay. But for this, we can basically just use the fact that real numbers can be approximated by rationals. So, okay, and then also maybe we need to use some kind of compactness or something. So what I'll do is I'll take, like, let's say C1, C2, dot, dot, dot. So I'm going to take a sequence of capacity functions, which are rational valued, and they converge to this one. So to be rational, capacity functions where the limit as n goes to infinity of Cn uv is CUV for all arcs UV. So for every Cn, so for every n, like this thing's rational, so max flow min cut is true, right? So if I let's say I let Fn be a max flow for Cn and Un be a min cut for Cn. There is something a little bit awkward here, though, that like as n changes, the set Un might change, right? Like there's no reason why. I mean, so the min cut could be over here, and now it's over here, and now it's over here, and now it's over here, and like it just keeps jumping around the graph, which would be kind of annoying, because then how am I going to find, like I would like to use these min cuts to find a min cut for C, but it keeps jumping. I mean, how could I do that, right? But then there's like a silly thing that like, okay, well, I mean, the graph is finite. So there's some set U that appears as the set Un for infinitely many n. Right, so like, and then we could just assume, we can just think of restricting to that subsequence of n and just assume that's what we were dealing with from the beginning. Like, so some U in the vertex set appears as the set Un for infinitely many n. Okay. We could just restrict ourselves to that subsequence, and then all of the UNs are the same, right? We just assume we just remove all of the other like values of n that are not in that subsequence. And still, these things are converging to C, and now actually like the same set is always the min cut. And then it's not hard to see that, you know, the capacity. So we know that for for all n, the value of Fn is like the kind of Cn capacity, I guess, of U. So once we've restricted to this subsequence, all of the UNs are U. And yeah. So, and this converges to the capacity of U. Now there is another bit of awkwardness. Actually, these flows might not converge. Like I would like to say that the flow function on the arcs would just converge. It might not converge though, right? Because I don't know, maybe my graph is like this. And maybe this path has the same capacity as this one. And maybe half of the Fn pushes all the flow this way, and half of the time it pushes all the flow that way, right? So then the flow function's not converging because it's switching between two different kind of things. But now you can use compactness. So okay, I don't know what your guys' like analysis and topology and stuff background is, but like, Do you guys know the word compactness? Or, okay. Right, okay, so, yeah. So we know that like Fn, if I took the sequence, well, yeah, the vector so we know that this is in well, I mean, I could have made this this convergence going from, let's say it's going from below, so these numbers are less than this one. So then, if I took the vector of all of the flow values, like they're all at most the capacity or whatever, and this is a compact set, because it's closed and bounded. If you don't know what compact means, it just means closed and bounded in this context. And yeah, these are closed intervals, so it's definitely closed and it's definitely bounded, right? And if you take any sequence in a compact set, it always has a convergent subsequence. So has a convergent subsequence. And we can let f be the limit. Okay, and then it's not hard to see that, you know, f will be a max flow. Well, it will be a flow of value equal to the capacity of the set U. Okay, so then, in other words, like the max flow is the min cut again. Okay. Okay, that was like slightly annoying to have to, you know, approximate by rationals and like take limits and stuff. But anyway, yeah, it's kind of just an analysis exercise, right? Any questions about that? Okay. So then let's come up with an algorithm for the max flow min cut. Well, I'm not coming up with it myself, but let's write down an algorithm. So like max flow min cut, the max flow problem, I think I mentioned before that it can just be reduced to solving a linear program. All the constraints are very linear and stuff, and the objective function is linear. So if you wanted to solve the max flow problem in polynomial time, you could just plug it into an NLP solver. But it's also nice to have an explicit combinatorial algorithm as well. So what we're going to talk about is something called the Ford-Fulkerson algorithm. Okay, so the idea of this algorithm, you're given a digraph, two vertices, and a capacity function. You want to find the max flow. So okay. The idea of this algorithm is basically that it's going to sort of iteratively find, like you're going to have some starting flow, which is going to be just the zero function. So the idea is like start with the flow f, maybe I'll call it f0, that just maps so every arc goes to 0. Okay, so that'll satisfy the conditions of a flow, but obviously the value of this flow 0, which is not very good. And then we're going to basically repeatedly try to increase the value to get a better flow until at some point we can't do it. And so when we can't do it, what we're going to try to do is then output a min cut. Okay, so, or a cut with the same capacity as the value of the current flow. So we repeatedly apply a flow, so I'll call this like a flow augmentation algorithm where for the flow augmentation algorithm, the input is a digraph D, 2 vertices, capacity function, F. So in the max flow problem, you don't have a kind of capacity function C and a flow F. Sorry. And the idea is either to find a better flow or find a cut of the same value as F. So our goal is to find a flow F prime of higher value, or an ST cut of capacity equal to the value of F. Okay, and if you can find this ST cut with that capacity, then that there is no better flow, and so you're done, right? Okay. So, and basically we're going to keep applying this this augmentation algorithm over and over and over until we get the best flow. Any questions about that? I mean, I haven't told you the algorithm, but yeah. It's actually quite a nice algorithm. It's, yeah, kind of clever and simple once you see it. So I feel like it could be good to have an example. I didn't prepare any, but, well, let's see what happens. So let's say in green I'll write capacities. And let's say our current flow values are like 1, 1, 1, 1 or something. This is S, that's T. Okay. In this example, I guess it's pretty clear what you want to do. Like if I wanted to get a better flow, if I tried to go this way and like increase the amount of flow out that way, I'm stuck. I can't do anything. It's because this edge is at full capacity. So like, there's no point even trying to bother with that. And also, even though this one's not at full capacity, it's going to be kind of useless as well because, I mean, to make that one high, the flow higher here, you'd have to make it higher here. It's not going to work, right? But yeah, this way you can shift things up, right? So, I mean, what you should probably do is just make this 2 and 2, right? And then that's fairly clearly going to be the max flow. And actually, if you wanted to see it's the max flow, you could find, well, I'm pretty sure this is going to be your min cut, right? Because, yeah, the amount of capacity leaving that set is going to be 3, right? Okay, but so like here's one obvious thing. If there's some path from S to T where all the edges on that path are below capacity, you should just push them up, right? Just by whatever I can so that none of them go above. So just take the minimum gap and just like increase it by that much, right? That's maybe kind of obvious. There's one less obvious thing though that can happen. And let's see if I can draw it. Okay, so maybe. Okay, so far it's got 3 coming in. Should have come up with this in advance. Okay, this is looking pretty. Oh no, yeah, this is okay. This is a good example, I think. But have I messed it up? Slightly, I have. I need to make that 4. I've got 3 coming in. Sorry, 4 coming in here. These should have been 4s. This could be a 5. Okay. Yeah, let's say capacity is green and flow is is white. So the white number should always be less than or equal to the green numbers. But it's got 3 that way and 1 that way. So it needs to have 4 coming. Oh, yeah, okay. I was reading the wrong numbers. You're right. Thanks. So sorry. Okay, I think 50% chance I've got this right now, but maybe. Is there a vertex that's bad? Actually, what's my flow out? 3 out. Oh yeah, there's no way. Oh no, yeah, I've got 4 in minus 1, 3 in. I think this might be okay now. Okay. This might seem kind of like there's not much you can do. Pretty much every edge is tight here. You can't just start increasing capacity or increasing flow values all over the place because like look, I mean, that's 1 1, 3 3, 4 4, 1 1. That one's got a little bit of space. But what am I going to do? I mean, you could want to increase that value. But what are you going to do? Are you going to take a path from there to there? There's only one path going along that edge, and none of these ones can be increased. But there is something else you can do. You can actually get a better flow. Can anyone see what you would do? So I think I can get a flow of 4 in total. Yeah? Yeah, so like, so this one, right? So this increases by 1, right? But then what else?
The second free, like the one in the middle.
That one. Yeah, this one I don't think I can do. So this one, it would want you to go, like the problem here is this one has flow in 4 and out 3. I cannot increase that one, but I can reduce that one. So you see what happened there? I increased this one, which made more flow into that vertex. You could either make more flow coming out, or you can make less flow coming in to make him happy, right? So those are two kind of operations you're going to want to do. That you may want to, yeah. If you increase the flow into some vertex, you need to either increase the flow out, or just decrease the flow coming in, and then it'll be okay. Okay. I don't know if that helped or not, but let's give the proof. Let's explain the algorithm. So what I'm going to do is so I take my digraph D and my flow F, and I'm going to make a new digraph DF be the digraph where so the vertex set of DF is equal to the vertex set of D, and for each arc in D, we add, so the edge, the arc UV, we add it to DF if that arc has some spare capacity. So meaning if currently the flow value on that arc is less than the capacity. Okay. This is kind of like indicating that's an edge that could go up, But now I also want to have something to indicate when an edge could go down. Because like we saw in this example, sometimes you want things to go up, sometimes you want them to go down, right? So I'm going to add the arc VU to DF. So it's like the reverse of that one. If FUV is bigger than 0. Because if it's bigger than 0, it has some space to go down if I wanted it to. I can't go negative, but I can go to 0, right? So to be clear, one arc from D might actually end up as 2 different arcs. Because maybe if both of these conditions are satisfied, then I would add UV and VU. So yeah, it might end up having things like this. Okay, so the first step of the algorithm is build this digraph, which you could just do by, and then the second thing is to search in this digraph to find a path from S to T. So find a path in DF from S to T if it exists. So we're going to have 2 cases. Either the path exists or it doesn't. So case 1, suppose the path exists. Okay, so this is in my graph, my digraph DF. And now in the digraph D, like all the arcs of this path in DF, they kind of exist in D, but some of them might be backwards, right? Because, to go from D to DF, I put some arcs the correct way, some backwards, some both, right? So really, this corresponds to a kind of a path in D, but where, yeah, some of the things are going backwards. So for example, it could look like this. Okay. So basically, here's what I'm going to do. I'm going to try to get a higher flow value. So like if I look at the first arc of the path and say, I mean, does it have the same orientation or different orientation as D? If it's the same orientation, what that means is that this arc could have its flow value increased a little bit. Because when two things have the same orientation, D and DF, that means that they have some capacity available, right? So imagine what I would do is on my first arc, I increase this capacity a little bit. The second arc is the wrong direction, but that means it can go down a little bit. So I would decrease that one a little bit. So I pick some kind of epsilon to be like the smallest kind of, okay, well, let's say I could pick epsilon 1. So to be the minimum of CUV minus F of UV such that UV is an arc of the original digraph and UV is in the path. I could define like epsilon 2 to be the minimum of F of UV such that, again, UV is an arc of the digraph, and this time VU is in the path. Then I could take epsilon to be the minimum of epsilon 1 and epsilon 2. Okay. But, okay, this is just notation, but like what I'm really saying here is epsilon 1 is the amount I could shift up the things on the path that have excess capacity, right? And then epsilon 2 is the amount I could shift down on the arcs that are like pointing the opposite direction. And yeah, so epsilon is going to be positive. And yeah, everything on this arc, or on this path, so if it's in the direction in both digraphs, I add an epsilon. If it's in the opposite direction, I minus an epsilon to the flow value. Okay. And now if you check, all of the vertices are still going to be happy. Like, the amount of flow in or out of each vertex is going to be, it's still going to be 0. Or the amount of flow in will equal the amount of flow out. And because I chose these carefully, all of the capacities are still respected, and nothing went to negative. So yeah, here I get a bigger flow value. Is the idea clear? Or okay. I think it's kind of a clever idea, this putting the edges backwards and stuff. Okay, so when the path exists, we can find a bigger flow. When the path doesn't exist, so case 2 is that no path from S to T exists in DF. Okay. Okay, now we need to find a cut where the value of that cut's the same as the value of F. It's not actually too hard to see what to do. just let U be all vertices, but be the set of vertices that can be reached from, maybe I'll say from S in DF. So when I say it can be reached, I mean using a path. Okay, so then clearly S is in U, and T is not in U, because if T was in U, that would give me the path, right? So this is an ST cut. Okay. Okay. So this picture is now in the digraph D. So in the digraph D, this set U has some edges going out, some arcs going in, whatever, right? There's some combination of this. But here's the thing. In DF, I know that this arc, this one that's going out, it's not going out in DF. Because if it was, I could, if I can reach everything in U from S, and if this arc was pointing outward in DF, I could just follow it and reach something else. So any arc UV in this like boundary plus of U, it must satisfy f of UV equals C of UV. It must be at full capacity, because otherwise it'd be pointing that way. Because that's our like definition. If it wasn't at full capacity, it would exist in DF. And similarly, any arc UV in this like minus boundary of U must satisfy f of UV equals 0. So all of these ones must have flow value 0. Otherwise, the opposite edge would be in DF, and I could reach something outside of S. Okay. So now if I sum over all the like flow values entering and exiting U, it's just going to count up all these capacities, and it'll have 0 for those ones. So, and that's going to also equal the flow out of, so yeah. So the value of F is going to be the sum here I'm using the thing we derived earlier. For any flow F, we kind of came up with this formula for any ST cut. And so this is just going to equal the capacity of the cut. Okay. So yeah, in the case where no path exists in DF, you would just output this cut, and that's a certificate that there's no bigger flow. Okay. And yeah, going from here to here is just using that all of these are equal to the capacity, and all of these are equal to 0 because of how DF was defined. Okay. Oh yeah, okay, so that, I guess I drew a square. We weren't really proving anything. I was describing an algorithm. But anyway, so this algorithm yeah, it does either increase the flow value or it outputs a better, or sorry, it outputs a minimum cut. Any questions about that? Yeah.
Just curious, what's the running time of this algorithm?
That's a perfect question because that's what I wanted to talk about next. So actually, the running time sucks in some sense. It's actually really, really, really bad. You can actually cook up examples where the running time is going to be infinity. Even so, like you got a finite digraph, no infinite, like just a finite digraph with capacities. You can make the running time infinity. Okay, technically, if the capacities are rational, I think it'll definitely terminate in a finite amount of time. If you use irrational numbers and you cook up the right example, it'll run forever, which is not good. And even if you run have a very small digraph with very simple capacities, you can make it run for a long time, as long as you want. So, like even using rational numbers, even using integers, right? So, like, here's a bad example. So, here's the thing. If you were smart trying to find a max flow here, you would just send n flow that way and n that way. But here's the thing. This Ford-Fulkerson algorithm, it just chose any path, right? If it can find a path, it just chooses it. It doesn't care what path it chooses. So at the beginning, we have a flow of 0 everywhere. Oh, maybe I'm going to make it green to be consistent with what I did before. And 1. Okay, so the thing is, if you ran this algorithm and you weren't careful, it might first augment along that path. So it might go, and then it's just going to increase by 1, right? So it's going to go 1, 1, 1. Okay. If you do that, then in the DF thing, you're going to have this way only, both ways, that way only. I think that this will be your DF thing after doing one step. And then it might find this path. It might go, oh, I see a path. It's this way up and then over. I mean, of course, it could have done that, but it might not, right? And then if it does that, what it's going to do is it's going to increase this one to 1. It's going to decrease that one to 0. And it's going to increase this one to 1. Okay, and then it might find this path. Increase by 1. It might find this path, increase by 1, increase by 1. And it'll just keep doing this for n, or like 2n steps or something. So yeah, even on a diagram with 5 arcs, it might take 2n steps, which is not good. Okay. Yeah. Well, one better way is to just run a linear program, but another better way is actually to do this algorithm, but choose the path more smartly, more wisely. So if you choose, it turns out if you always choose a path with the least number of arcs, then you can make a better running time. So I'm going to try to explain that. I'm not sure if I've got time to, but let's kind of see how that works. So in the Ford-Fulkerson algorithm, if you always augment along paths with the minimum number of arcs, So, like, I mean, when I say paths, I mean paths in this df thing. Then the running time is big O of the number of arcs squared times the number of vertices. Okay. So in this example, the problem is we keep like, even though there was like a nice augmenting path with 2 arcs, we kept picking 3. And we kept augmenting, like we kept picking 3 arc augmenting paths. But if you pick the shortest one, you can see that this would go really fast, right? It'd be like, it'd give me, I do n, and I win, right?
It can be like a similar example where we've done like switch between two shortest paths. Able to kind of do the same thing. Is there?
Apparently not, because yeah, I'm going to try to prove. If there is, then we have a problem, because then math is inconsistent. But no, yeah, no, there's not going to be. So if we use shortest paths, it's going to turn out that, yeah, for some reason you cannot make an example like that. Yeah. So let me try to prove that. So here, like, this is much better than in that. Like in this situation, the number of iterations was like, it could be anything, even for just 5 arcs, right? So it's independent of the number of arcs. But here I'm saying now it's going to be bounded in terms of the digraph. Okay. Okay. Well, here's one observation. So each iteration of the flow augmenting algorithm it certainly takes time, big O of the number of arcs in the digraph. Okay, and the reason I'm saying this is so then what we need to show, so if this is true, so we can talk about this in a second, but then all we need to show is that the number of iterations is big O of the number of vertices times the number of arcs. Okay. So why does each iteration take this time? Well, I mean, to construct the DF, it'll take about, you have to inspect every arc once, right, to see if it's at capacity or if it's at 0. And then you want to search for a path from S to T. And if you just explore the arcs going out, kind of in a kind of breadth first search way or something, you can find the shortest path from S, shortest in terms of number of arcs path from S to T. And you might have to explore all of the arcs, but not more than that, right? So yeah, each iteration of the flow of the augmentation thing takes that much time. So we just have to show that you will not have to augment more than that many times. Number of vertices times number of arcs. Okay. Okay, so given a flow F, so suppose we're in, I'm going to, well, yeah. So I'm going to just write dist F, so dist for like distance, be the minimum number of arcs in a path from S to T in df, and let E sub f, what am I putting? Be the set of all arcs on such a path. When I say such a path, I mean a minimum one. So, like, okay. So, what I'm going to prove is that, so if, let's say, f prime is the flow we get out of the augmentation algorithm, so applied to f, then either this dist of f prime will be bigger than dist of f, or it'll be equal but the this E thing, E of f prime, will be a strict subset of E of f. So this is subset and not equal to. Okay. It's not clear at this moment what the point of this is, but oh yeah, maybe I should say these are the arcs. I guess maybe it's clear because I'm in df, but yeah, in df on such a path. Okay. So, okay, this is what I'm going to prove, but maybe first let's talk about what the point of that is and why that bounds the number of iterations. So if this is true, oh, and by the way, this is applying the augmentation algorithm where we pick a shortest path, right? We have to augment along the shortest path. So if this is true, then if I look at the quantity dist f, or the pair dist f comma number of arcs of D minus E of f. So if I look at this kind of ordered pair, this is always going to increase lexicographically in each iteration. So in each, when I say iteration, I mean application of the augmentation algorithm. So when I say lexicographically, I mean, like if this was a word, this would come, if every time I apply the augmentation algorithm, the word I get, the new word, will come later in the dictionary. Like either this number will be bigger, I mean, that's what we said, either that number will be bigger, or the two, it'll be the same, but the EF prime set will be smaller, which makes this number bigger. But then if this keeps increasing lexicographically, like you will never have the same pair show up twice. Right? And there's only like number of vertices, different choices for this. And there's only like number of arcs, different choices of this, and they never appear twice. So yeah. So I haven't proved that this happens yet, but so the pairs dist f and this thing never repeat, and so the number of iterations will be at most the number of choices for that, which is just a number between, let's say, I don't know, 1 and the number of vertices minus 1 or something. And that's also just a number between, let's say, 0 and the number of arcs, right? Okay. Is it clear why this would give us what we want? I don't know. Do you know what I mean by increases lexicographically? So either the first entry increases or it stays the same, and the second entry increases. Okay. All right, so I need to prove this. So, yeah, so recall f prime is obtained from f by augmenting on a shortest path, right? Because that's our only modification right now. We're only taking shortest path, let's say P from S to T in DF, right? Okay. So what's going to happen? Like, what is the difference between DF and DF prime? Like, they're almost the same, except that, like, for this path P, like I increased and decreased a bunch of flow values on this path P, right? So like, but all of the other arcs will be the same in DF and DF prime, but maybe like some arcs of this path P that were like not at capacity or not at 0, maybe they become at 0 or capacity. Like the things on P got shifted. So basically, DF prime is the same as DF, except some arcs of P now go backwards from what they did before. Like some of those arcs get switched. So it's similar to DF, except some arcs of P, like they may be pointing in different directions, or maybe in DF there was only one arc, and now in DF prime there's like both of them. Like basically things on P have changed, right? So maybe different. So, okay. So I'm going to let let D star be the digraph obtained from DF by adding the reverse of every arc on the path P. So then, of course, DF and DF prime are subgraphs or subdigraphs of D star. Okay, because like the only difference between these things is that some of the arcs on P were going in different directions, but now I've just made a digraph D star where I've got both directions for every arc on P. So, okay. Okay, and let E star, well, basically I want to let E star be like this EF thing, but for D star, okay? So these are the arcs on a shortest path in D star from S to T. Okay, almost done. So my claim is D star cannot contain a path Q of length at most this dist F thing, which uses an arc yeah, that is not in EF. Okay. 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 If it did, like, do I mean EF? Yeah, I think I do. So if it did, then it must use one of these new arcs that we added. So when we went from DF to D star, we added these backwards things. So it must use some arc, let's say VU, where UV is in P. Like it must use one of these arcs that was like added in the construction of D star. But now let's, so let's say let VU be the last such, the latest such arc in Q. Okay, and here's just the picture to finish it. So let's say this is the path Q. That's VU. But if I look at the path P goes through UV because the only extra arcs, that we added were the ones that were like reversing an arc that was on P. So like the arc VU, because was one of these ones we added, it must be the reverse of something that was on P. So the path P kind of looks like this. It goes to here, it goes to U, it goes to V, and it goes over. But now I get a shorter path by just going from S to the first time, well, to when P reaches U, and then kind of going across like that. Or you could follow Q this way, or anyway. Oh yeah, and then follow the end of P that way. So yeah, that gives you a shorter path. In the original digraph, because I didn't use the edge BU in that, which would be a contradiction. Okay. Since D star can't contain any such path, neither can df prime. Okay, so this actually proves that thing, because either df prime doesn't have a path of that length, in which case the distance went up, or it's and all of the arcs of df prime are in of ef prime are in ef, because that's what this would imply, except there's going to be one that isn't. It's the one that got switched when I augmented p. Okay, that's all a bit complicated, but the key thing is that this can be done in polynomial time. So that answers your question finally.